We come to our next speaker. This is Professor Anette Müllertz. She's a professor at the Department of Pharmacy at the Faculty of Health and Medical Science at the Technical University in Copenhagen. And we will switch gear a little bit. The last two talks was about parenteral application, and now we move to oral application. And the title of our talk is Elucidating the Use of Lyso-lipids in all self-nanoemulsifying drug delivery systems.
I am gonna, as Simon just said, gonna switch gears a little and talk about oral drug delivery, and there's actually a good reason for that. I know that all around here at the Cleanarm it seems to be quite a lot of parenterals, but when you look at it, there is actually about 50% of all the drugs that are dosed are oral, so therefore I think I can justify that I mainly work with oral drug delivery. And then, of course, one thing is oral drug delivery, but what I also am going to talk about here is lipid-based drug delivery, and that also has a very good justification because lipids are a very essential part of our diet. The body is super well equipped for lipid digestion. We have about 95% of what lipid you ingest is actually absorbed. That also gives us problems in some cases. And one other thing it does is that for some of these poorly soluble drugs also give increased absorption. The drug have what you call a food effect. Here's an example. There's a lot of drugs that have this, and what you see there on the left is an example of cinnarizine in a clinical study that we recently did, where you see that we actually in the fed state get a much increased absorption. And then, of course, in that light, lipid-based formulations would be relevant, but at the same time, it would also be relevant to actually use natural surfactant. And that's why lyso-phospholipid is attractive in that regard, because the way you usually do lipid-based formulations is that you have an oil, you have a hydrophilic surfactant, and the hydrophilic surfactant is often an artificial, synthetic surfactant such as colifor, tween, lebrosol, or something that's not exactly natural. So if we can reduce the amount of that and instead use lyso-phospholipid, it would be an advantage. And maybe I need to say here also that these self-nanoemulsifying drug delivery systems that I work with are characterized with that they are isotropic by nature. When you mix the lipids together, they form an isotropic solution that can be filled into gelatin capsules. And when they are then dispersed, for example, in the gastric fluid after ingestion, then they will form a nanoemulsion droplet where you have the hydrophilic or surfactant and also the lipophilic surfactant, where I would categorize the lyso-phospholipid on the surface of the droplet. What you want to take care of in that regard is that the drug precipitates out of the solution, because then you're back where you started with a crystalline drug. When we are developing these formulations, we usually use a DOE approach, and then we identify the excipients with the highest solubility. We do a design of experiment. We make all these formulations, and then we measure the droplet size after we disperse them. And the definition of nanoemulsion, more or less, is that we want it to be below 200 nanometers. So that's basically what we're looking at. So we did some studies some years ago where we tried to see how much lyso-phospholipid can we actually load into these lipid systems and still have an emulsion that's below 200 nanometers. And we found that this will also depend on the rest of the excipients in the SNET system. And when it is medium chain, which are medium chain lipids are easier to emulsify, then we can actually include up to 40% of lyso-phospholipid in the formulation, whereas if it is long chain, we can only include between 25 or up to 30% under some circumstances. But if we include too much, then we will have an increasing droplet size because of the nature of the lyso-phospholipid. It has a very little hydrophilic group and then this long lipophilic tail. But one thing that you also have to consider with regard to lipid-based drug delivery systems is that they are digested, because, as I started out saying, they are part of what you eat on a daily basis, and therefore there will be digestion going on. So simple dissolution studies does not make sense. So therefore we are usually characterizing them by running an in vitro digestion study, where we simply simulate the composition of the gastrointestinal fluids. We add the relevant enzymes, and then we look at how fast is the formulation digested, and what is the fate of the drug. Is it solubilized, or does it precipitate during the digestion? All this provide relevant information as to the performance of the formulation. And one way we also carry out these studies is in a synchrotron beamline. So we basically place our digesting vessels in the beamline room, and then we have a capillary with a flow through, and then we can inline or online look at what kind of colloidal structures are formed during the digestion. And we did this here with this is actually what you see with the SNETs where there's no lysophospholipid present. This is a simple SNETs containing medium chain glycerides, and also labrosol, which is pegylated medium chain fatty acids. And this is a formulation that forms a droplet size of around 50 nanometers or something like that. When we digest that, before we digest it, it's basically just lipid droplets. When we digest it, then we have the formation of vesicles, and we see that we end up with multilaminar vesicles after at least 1 hour of digestion, and we also see that reflected in the Bragg peak that you see there at 2Q. So basically, we see the formation of multilaminar phases when we digest the SNETs in general. When we add lysophospholipid, in this case we have 30% lysophospholipid in the system, then funnily enough, we don't see the multilaminar phases. We only see mono, or basically not, we only see mono and bilaminar phases. So we basically have the Bragg peak eliminated. There's no Bragg peak in these systems. So that's like an interesting fact, and that's just what happens. And then, of course, the important thing is, so what does that actually mean for the absorption of a drug, for the bioavailability of a drug? So we did, first I want to just sum up what I just said, but I'll go quickly on to say that what we see then in a pharmacokinetic study in the rat, unfortunately, for the students who did the study, she was very frustrated. There is actually no difference, as you can see here. The two pink curves, which are the SNETs with and without LPC, there is a tiny tendency for a better and prolonged absorption, but there's no significance here. So no in vivo effect, at least when we were using fenofibrate as our model drug. But the interesting thing that I want to say here, and what you should pay attention to in this graph, is the black stipulated curve, because that's basically a soybean oil containing 30% of lysophospholipid. And by doing that, we actually end up getting exactly the same absorption or bioavailability as we do by making the SNETs. So in that way, in this case, and again, emphasizing fenofibrate, which is a very lipophilic drug. When you do that, you don't really need to develop a SNETs or anything. It's actually enough just to add the lysophospholipid on top of an oil, and you'll get the same amount of drug absorption. So that was actually pretty cool in that regard. And also, you can also turn it around and see, no, we didn't see an improved absorption of the lysophospholipid containing SNETs, but we also didn't see a reduction. So in that way, we can replace artificial or synthetic surfactant with natural surfactant and get the same amount of absorption. Another way we've been looking at the use of Lyso-phospholipids is to make a complex with a drug that is not lipophilic and does not dissolve in SNETs. Such a drug is amphotericin B. And as you might know, this is an antifungal drug, and there's actually not an oral product available. It's only available as an IV product in different also liposomes and different kind of formulations, which is super expensive and not very convenient for the patients, because often they are living in developing countries, people with invasive fungal infections and so on. So an oral product is a very attractive formulation to have with this drug. But amphotericin B has basically no water solubility and no lipid solubility. It's basically what you would call a brick dust molecule. So therefore, we decided to try to make a lysophospholipid complex with the drug to make it more lipophilic, and that way being able to incorporate it into to a SNETs, or maybe just using the complex in itself. So we lyophilized the solution of MAPC and amphotericin B. That actually gives an amorphous formula or amorphous structure. So we basically can amorphize amphotericin B by doing that, and that also results in an increasing solubility of amphotericin B, as you can see here. And this is not due to only the lyso-phospholipid being present, because it doesn't happen if we increase the same amount of lysophospholipid without making the drug amorphous. So we continue in this case with the 1:3 ratio. And then we wanted to see, so how does this look? What kind of a complex do we have formed here? We could actually see that we get a big, when we just do simple dynamic light scattering, we do get a bigger size of this complex. So something is going on. We then did cryo-temp, and we could see these weird flexible rod-like string, rods on a string or something like structures in the cryo-temp. So we thought, really? That seems strange. So we had a chance to go to the ISIS, the neutron scattering facility in the UK, to run the samples there. And there we basically also, by doing the sand studies, we could see that what fits the curve that we got out of the complex was actually a cylinder or a flexible cylinder. So it basically fits with this strange rod on a string structure. I cannot really explain that, but it's kind of interesting that the amphotericin B lysophospholipid complex formed those kind of structures. But then what we really wanted to do was to see, or what we wanted to compare the complex was to use this to increase the load of amphotericin B in the SNETs. And here we could actually get at least up to 33 milligram of amphotericin B into the SNETs, whereas for the pure amphotericin B we could only dissolve like 1 milligram. So that was pretty cool, and we actually saw exactly the same droplets as we see with the original SNET, so no effect on that. And then we did bioavailability studies in rats, and what we get out of this is that the APC alone, the complex alone, doesn't really do anything, but when we have it in the SNETs, we get a significantly increased absorption. So we believe that we have here a potential new oral amphotericin B formulation that might also work in humans. We don't know yet, and obviously, first of all, we need to do fungal models, fungal studies to know that. The last example is just this one. This is nilotinib, an anti-cancer drug that also is completely impossible to put either in, it has no water solubility, no lipid solubility, like 4 milligrams per gram in lipids or something. So we thought, what about making a phospholipid complex with this particular drug? So also it has a super high food effect, and the bioavailability on the package of the drug is between 17% and 40%. So quite variable. So also here we did an oral gavage study in rats, and as you can see, if you look over there, the pure amorphous is the black curve over there, so you don't really get above a plasma concentration of 4. But when we then, like the dark blue and the dark green curve up there, which is the complex of phospholipid in the SNETs, then we actually get plasma levels up to 10 microgram per milliliter. So we get a significant increase in the absorption by having a phospholipid complex of nilotinib in the SNETs formulations. So definitely that is also a way of increasing absorption of the drug. So yes, lyso-phospholipid can be incorporated into SNETs. If we have lyso-phospholipid, we don't have multilaminar vesicles during digestion. Doesn't seem to mean a lot. But you can also make a complex of the lyso-phospholipid with a drug with a low lipid solubility. And then that also actually would go for peptides, which I didn't talk about here, but we have also used lyso-phospholipid to increase oral absorption of peptides. And here lyso-phospholipid has an additional advantage, as it is also a permease enhancer, and then it can that way increase absorption of oral peptides. So I want to thank my group who did the work. I want to thank the Phospholipid Consortium, or Phospholipid Research Center, for actually funding some of this work. And I want to thank you for your attention. And if you have any questions, please.
Yeah. Thank you, Anette, for this talk, which is now open for discussion. We have 2 minutes, so maybe 1 or 2 urgent questions. Are there any questions?
Thank you very much. Thanks a lot for your nice presentation. I have a question about because when we talk about, for example, formulation like Ambisome, there we have free amphotericin B inside the bilayer that can go through the exchange with the fungi, and then it's effective. So what do you think about the amphotericin B in a complex, and then to be functional? First, can it be delivered into the fungi, or also when it gets to the fungi? So is it effective as we are expecting, like free amphotericin B?
Well, the thing is that that's a very good question, and obviously I don't know, because we haven't done those fungi studies yet. The first step is just to see that yes, we can get it absorbed. Then you could think that when the amphotericin B actually in that amount get into the body, it will do what it needs to do, because you also cannot be sure that it does it when you put it in a liposome. And it also actually works in whatever it is, these taurocolate mice cells, right?
Is there any specific mechanism that can break it, this complex with the fungi, then to make it functional?
Yeah, but it is not. This is not a covalent binding. It's simply just adhesion. So it's on some unspecific binding, and I cannot exactly tell you what binding it is, but I'm sure that it's not covalently bound. So it's not a loose bind. It's not a very strict, difficult to break binding. And I'm not really sure exactly what form the drug is in the lipid formulation. I just know that it is in the amorphous form, so it did not form any crystals.
Thank you.